Um, it's great to see you here. Thanks everyone for coming. This is the last event of our University of Bristol Jean Golding Institute Data Week Online 2021. This is, I think, the 40th event over the 5 days, and we've just heard that we have hit 2,000 participants. That's actual people joining, not just people who've registered on Eventbrite, so actual people, which is an amazing achievement for the whole team and for the community that we serve. So thank you all for coming. Just a few housekeeping things. Oh, first of all, so my name is Kate Robson-Brown. I'm director of the Jean Golding Institute. So I get the kind of the special pleasure of kicking off the week and ending the week as well. A few housekeeping things. The session is being recorded. It would be great if you could confirm that you've read through the JGI Code of Conduct. If you haven't managed to read it, then Lily's going to put a link in the chat for you now. If we could mute our microphones while the talks are going on, unless stated otherwise by the presenter or speaker or me, the chair. It would be great if you can complete the registration and feedback forms. I mean, the feedback particularly is really useful to us because it tells us what you've enjoyed, what do you think we could do differently, or if you have any suggestions for future events of the kinds of things you'd like us to engage with, that's really, really helpful for our planning. And we don't have that many opportunities for networking in this kind of remote environment. So let's make the most of what we do have. And it'd be great if you could introduce yourselves in the chat box, tell us your name, role, where you're from, and hopefully we can help you make some connections. We'd like to encourage us to all to use the Slido for Q&A for this session, for questions. So this is the code 982973, but we'll also put the link in the chat so that you can find that easily as well. So yeah, please do use the Slido, and we'll occasionally prompt you to do so through the afternoon, so you'll remember what we're up to. And most of you will already be friends of the Jean Golding Institute, but for those of you who are new, you're extremely welcome. It's great to have you here. It's always nice to reach out to find new people to join our community. We are one of 5 University of Bristol research institutes. The research institutes are constituted outside the faculties, so they all have a lot of independence in the ways in which they engage with the communities, but we share a remit of building multidisciplinary research communities for the topics that we support. In the case of the Jean Golding Institute, the JGI, we work in the areas of data science and data intensive research. And we have 4 strategic priority areas for the research that we support that you can see on this infographic on the left here. Those are the verticals: societal challenges, data visualization, materialization, realization more generally, reproducibility and data governance. So that would include the open data agenda, conversations around ethics and consented data use, those kinds of issues. And also fundamental and foundational research, which at the University of Bristol is largely found within the faculties of science and engineering. So for example, mathematics and statistics and computer science. The mechanisms of engagement for those 4 verticals are represented on this infographic by the horizontal pink arrows. So we've got all kinds of activities around developing communities. So for example, running this kind of event, hosting data competitions, engaging with PhD community through, for example, poster competitions and beauty of data competitions, and also by offering Seedcorn funding. So once a year, as many of you will know who are on this call, normally around November, we put out a call for new multidisciplinary collaborative pitches for modest amounts of funding that can kickstart a new activity in a safe space. So we want to encourage things like that, activities that are innovative and develop new connections. And of course, this event this afternoon is a celebration of the projects that we were able to support this year, recognizing this was obviously a particularly challenging year. And yet we've seen some incredibly innovative modes of working and new collaborations bringing research communities together. So it's been an absolute pleasure to be able to support those projects, and great to see you here this afternoon. The other horizontals you can see there, so for example, we have training and professional development throughout the year. So obviously, you know that we've put on a great deal of training opportunities for this data week, but in fact, we offer those kinds of opportunities throughout the year, many in collaboration with the ACRC, the Advanced Computing Research Centre in Bristol, but also with external partners and some bespoke events as well. So it's always worth keeping an eye on our website to find out what opportunities are available. We are the portal for the University of Bristol's relationship with the Alan Turing Institute. The Turing is the National Institute for Data Science and AI. I'm the Turing University lead. Patty Holly, who is the Institute manager, is also the University liaison manager for that relationship. And we work very closely with about 30 Turing Fellows within the University of Bristol, trying to make sure that all the opportunities that can be levered by membership of the Turing kind of reach out as far as possible. And we run a data science surgery service, which we call Ask JGI, where University of Bristol researchers can come to us with a data science query, and we can work with you to point you in the right direction. And sometimes those projects in themselves develop into much bigger activities and have long-term funding, and can engage with our data scientist team. So we have a team of data scientists and research software engineers in collaboration with ACRC who can be deployed on those kinds of projects. So some of them develop into these longer term projects as well. So you've seen a version of this before. This was, I should say, oh, I've been saying this is and this will be for weeks, but this was University of Bristol Data Week for this year, and we're right at the end there on the bottom right with our lightning talks. But as you can see, we've had a great number of talks over the week, 40-odd talks, including some lunchtime networking events. And you can see from the colour coding how that's kind of scattered across the week. We've tried to engage with research activities in all aspects of the data science pipeline, from generation of data all the way through to analytics and communications. So we hope there's been something for everyone there. And we wouldn't have been able to do any of it without the collaboration and support of our sponsors and collaborators. And we thank you all. You're part of the JGI family, the data science community of the university, the city, region, and nationally. We couldn't achieve this without you. So thank you very much for all your support. And there are lots of ways of staying in touch with us. You could join our Data Ethics Club, for example, which meets regularly sometimes as a journal club, sometimes for talks. We have a similar activity for data visualization that also meets monthly. You could look us up on Twitter and LinkedIn, subscribe to our newsletter, keep in touch via the JGI website and the blog, or even work with us to deliver a blog if you like. We also do that. And if Data Week has been really kind of exciting for you and you've enjoyed it, then I've got a plug for the next thing to have in your diary, which is the Showcase 2022. So that will happen between 17th and 18th of February. The face-to-face events will be down at the M Shed, which is the industrial museum in the city of Bristol, down by the harbour side. But we will also have blended events as well. And this will be a celebration of all things data science and data-intensive research, and involve lots of community-facing activities as well, and talks which will appropriate for public engagement. So do put it in your diary, and we look forward to seeing you there. So without any further ado, I'm going to stop showing my screen so I can see some faces in the room, which is great. We have an absolute jam-packed programme this afternoon of lightning talks from those funded research projects. The talks themselves are going to be about 15 minutes long, and then there will be a 5 minutes question and answer at the end, which I will chair. So if you write your questions in the chat, we'll collate them behind the scenes and try and get through as many as possible within that time. And so we're going to start off with a talk on the project Automating Food Aggregation for Nutrition and Health Research. And this is Dr. Zoe Tumpakari. She is a lecturer in nutrition and behaviour change. Her research focuses on how features of the eating environment, like where and with whom people eat, influence their food intake, and how these could be altered to improve the population's diet. In addition, her research explores the role of dietary and physical activity patterns in the prevention of cardiometabolic health. Over to you, Zoe.
Great. Thank you so much, Kate, for the introduction. So let me just share my screen. Okay, so everybody can see that? Can I see a nod? Yes, excellent. Thank you. So yes, so the really grateful for the funding that we got from the JGI to sort of look at automating food aggregation, which is really important, as I will explain in sort of diet research. So So grouping food items into food groups is an essential first step in dietary analysis, which aims to reduce data on thousands of individual food items to a more manageable set of food groups that have similar nutrient composition and culinary usage. And so if somebody records that they have eaten mango, apples, cherries, we group those items to sort of fresh fruit food group. Equally, if somebody has eaten bacon, ham, sausages, we group these food items to a sort of processed meat food group. We can then explore associations between these types of food groups and health and understand patterns of diet in the population. Grouping food items, however, is a challenging and very time-consuming activity. And to date, this has been mostly a manual task because of the complex decisions required around assigning food items to the correct food group. For example, if we have a spaghetti bolognese, should it be allocated to the cereal mixed dish food group because it has pasta, or should it be allocated to the meat mixed dishes group because of the minced meat? And decisions usually sort of we look at ingredients like percentage of meat and pasta in this case, nutrient composition, but also culinary usage. For example, we have puddings and confectionery. They're in different food groups. They're both high in sugar, but one is eaten as a meal or the other one is eaten as a snack respectively, and that may sort of give us different associations with patterns of diet that we're interested in. So a couple of years ago, there was another Jean Goulding Institute event where I met one of the current collaborators for this project who had access to Tesco club card data, specifically 1.6 million Tesco loyalty cards in London. And within those loyalty cards, there were 46,000 unique food items. So that's a very large scale data set. We're talking about naturalistic settings. So people actually have purchased these food items. It's not something that they recorded, and that has bias a lot of the time when people record what they ate. So we thought it would be good to use this data to first of all assign them to 51 predefined food groups that we have already used in previous analysis. These were generated in ALSPAC study, so the Children of the 90s cohort in Bristol. And using these food groups, we could then generate a dietary pattern score, as we call it. So a combination of all the food groups that gives a score depending on how optimal somebody's diet is, and then use that score to explore associations with health. So far, we have done this, the latter part of the analysis, in terms of we have used 51 food groups. We have generated a dietary pattern score and looked at associations with health in a UK representative sample of around 4,000 children, 4,000 adults. So that's the National Diet and Nutrition Survey that is happening every year. So NDNS for short. So that only has 4,000 food items, which I have previously manually allocated to these 51 food groups. However, when we want to assign the 46,000 food items to these 51 food groups, doing that manually is not possible. So therefore, the funding that we got was to develop a supervised machine learning algorithm, which will assign these 46,000 unique food items to the 51 predefined food groups. And once we have that, we can then replicate our previous analysis, and not only replicate it, but scale it up really, because we're going from around 8,000 people to 1.6 million people with the Tesco data. So that was the aim of the project. Just to give you a bit of context, these are the 51 food groups that we want to assign the food items. As you can see, they're quite detailed, and that's why decisions are not easy. So we have high fat and low fat milk. We have sort of high fiber cereal or other cereal, meat and poultry, meat mixed dishes, processed meat. So a lot of detail, and hence it's not easy to just say allocate all these food groups to X, all these food items to X food group. So in terms of the methods, there were 4 algorithms that were chosen for this based on their ability to classify text. So essentially we have the name of a food item, that is a text, and we want to classify this text to a food group. There was a brilliant PhD student who did this for me. I'm a dietitian by background, so for me that was a very new information. So for each of those 4 algorithms, there were 3 stages that were followed. The first one was building a dictionary of words taken from a reference data set. So that was the NDNS data set that I had previously used to manually allocate food items to food groups, and the Tesco data set. Then we trained the algorithm based on the reference data set, and then we sort of classified food items in Tesco data, but also in the reference data set, so that we can see how the algorithm performed, just because we knew the outcome and we could sort of compare. So in terms of the first stage, we used both the training data set, so NDNS, and the Tesco data set to sort of build this dictionary. And if you think that in this case, we only have 2 food items, and there is a column that talks about ingredients. So if we remove special characters, white spaces, duplicates, and things, we get essentially a sort of, that is the dictionary that comes from these 2 food items, Barilla, arrabbiata sauce, and so on. Obviously, we had thousands of food items, hence the dictionary consists of thousands of words, but that was the first step. Then we used the reference and DNS dataset to train the algorithm. So as I said before, 4,000 food items in NDNS, which I had manually allocated to these 51 food groups. So we started with the dictionary. As an example, let's say that the dictionary only contains 10 words, although this wasn't the case, it contained thousands of words. And the food item that we want to classify to a food group is called cauliflower and potato curry. So after the keyword process, the item becomes cauliflower potato curry. And then we mapped these 3 keywords into the dictionary. So the output gives us either a 0 if it doesn't identify a word in the dictionary, or a 1 if it does. So in this case, the 3rd place is cauliflower, and it identified the cauliflower from the keyword, and it gave us a 1. And then our 6th and 7th place, potato and curry. So once we have that, and we know what is the associated food group, so based on my manual allocation, I had allocated cauliflower and potato curry as a vegetable mixed dishes food group. And then the training vector gives us the keyword plus the associated sort of food group, that is vegetable mixed dishes. So at the end, one training vector is created for every food item. And the set of all these training vectors are used to train the algorithm. So then the next stage is classify the data set. And we did this in the NDNS data set, so the reference data set. And then we could compare whether the algorithm performed well by predicting the food group. And the Tesco data set that we want to eventually classify the food items. So if, again, the food item that we want to classify is cauliflower and potato curry, we map the keywords into the dictionary as before. And then we use a train algorithm to predict the food group that cauliflower and potato curry belongs to. as I said, there are 51 food groups from 1 to 51. So then the output that we get gives us percentages of certainty that cauliflower and potato curry belongs to each of the 51 food groups. So in this case, for example, there is 99% certainty that cauliflower and potato curry belongs to vegetable mixed dishes, and 1% that it belongs to vegetables raw or boiled. And that would be 51 certainty values here in this vector. So the output that I eventually get and I use is for each food item, I get the two highest certainties, in this case 99%, and the food groups that these certainties sort of predict. So that was the process that was followed, and that was followed for all these sort of 4 algorithms. And eventually, in terms of precision and accuracy, neural networks were decided as having the best performance, and that was the algorithm that we used in the end. So when we classified the reference data set, so we removed all the food groups that I had manually allocated, and we had the algorithm predicting the food groups that each of the food items belonged to. So out of the 4,000 food items, 3,900 were correctly classified by the algorithm. So the algorithm was 96% accurate in the reference data set. So that was really good. I think when I asked sort of people from computer science, they said it's amazing. Apparently anything above 85% is considered excellent. So that's great news. So I wanted, though, to explore the food items that were not correctly classified. I wanted to explore why that may be, so that possibly that can inform what we can expect in the Tesco data, because we don't know, we don't have an allocation, so we just have to trust the algorithm in a way. So out of the 143 food items that were not correctly classified, the majority belonged to chocolate and confectionery, puddings, sugar sweetened beverages, and so on. So there was the argument that potentially the algorithm, if a food group has only a few food items, the algorithm cannot learn a lot from that food group because it just has very limited information. So then I checked whether these food groups had few items in them. So that meant that the algorithm possibly couldn't learn a lot. And that's why I wasn't able to classify these food items correctly. That wasn't the case. So as you can see, the food items in each of these food groups was quite high. So the range was from 4 to 300. And all these food groups had sort of around 100 food items each. So that argument wasn't sort of standing. In terms of certainty values that I said we get from the output, the median certainty value in the reference and the Tesco data set was really good, so 99% and 92%, and there was minimum and maximum, but the range was very similar. So in terms of sort of next steps, we have, the algorithm has predicted the food groups, and I'm thinking of that it would be good practice to select a section from the Tesco data set and manually allocate the food items myself, so that then I can see whether the algorithm predicted them correctly, so that sort of I can see its performance. However, some limitations that potentially may limit the algorithm doing as well in the Tesco data set is that we did not use nutritional values to sort of inform the classification because the data was not complete. Data cleaning could have been done better just because we did not have much time to complete the project. Some decisions around singular versus plural, so apple with one P, that was not cleaned properly. And potentially overtrain of the algorithm. So in MDNS, it learned a lot from similar food items. So when the algorithm goes to classify food items in the Tesco data set, these are completely different food items. It might have a sort of issue there because it has learned a lot of similarity from the reference. And also the fact that there was an uneven number of food items in each food group may also potentially have issues in the classification in the Tesco dataset. So thank you very much. Any questions, any feedback, how to make this better would be much appreciated. And just to say thanks to my amazing team, collaborators, Ivan, Hugo, Luca, and Daniela for the data and for their work in this. Thank you very much.
Thank you. Sorry, that's great and absolutely bang on time. Yeah, we do have at least one question, which is around whether or not you can see from your process how food items cluster. So do food items and categories cluster? Can you predict food purchases from kind of individual foods purchased? You see what I mean?
Yeah, you mean sort of if we have individual food items, if we can predict what food groups people bought? Is that what you're asking, Kate? Possibly, but because there's so many food items and they're so different and they vary, that's why we sort of need to have food groups and work with those. But they vary so much, so it's very hard to predict sort of food groups, and that's why we sort of need to make the algorithm as good as possible so that we don't have to do any manual checking there, just because it's not possible. We're talking about large data.
Kind of collateral data on the types of food items. So, for example, are you able to kind of drill down to, for vegetables, how the packaging works? So, are some of them loose and some of them in boxes, that kind of thing?
Yes. So Tesco data has, in the description of the food item, it may have information about sort of loose or have a kilo or things like that, so we can infer from that. But and that possibly would be useful information in terms of if it says vegetables and a quantity, for example, we know that it's a raw vegetable, so that could inform the allocation rather than a sort of vegetable mixed dish that wouldn't be measured this way. So that would be useful in the allocation, but that wasn't considered here because the reference data set did not have this information.
Sure. There's one more question. When looking at ingredient labels of processed foods, did you take into account the order as top ingredients in terms of quantity are listed first?
Unfortunately, no. Anything in terms of quantity, because it was not complete data, we did not take into account because it would just sort of create issues for the algorithm. And that, unfortunately, we would expect that in Tesco, we would have this information, but we don't. There is this information for some food items, but not for all of them. So unfortunately, we do not use it.
Feels like a treasure trove of information and really great to kind of see your process and where you're going with the project. Thank you so much.
You're very welcome. No, that was really useful, and thank you as well.
Okay, so moving on. Our second presentation is on the project, How Many Simulations Do You Need? Artificial Intelligence in Clinical Trial Management, and we're welcoming our colleague Xin Fei to present this. So Xin is a lecturer here at Bristol in the School of Management. Before that, was a research fellow at Warwick Business School, has a degree in PhD in Management Science from Warwick and a BSc in Physics and an MSc in Financial Engineering. Research interest lies in the fields of efficient information collection, stochastic optimization, transportation management, digital health and pharmaceutical supply chain. So, Xin, are you, yeah, I see you there. Welcome. Hi, over to you.
Hi, good afternoon, everyone. Let me find the button to share my screen.
Should be down the bottom, normally down the bottom in green.
Oh, okay.
Yeah?
Yeah. Yes, I think this one. Hold on, I need to change the system setup.
Not to worry. Every platform has its quirks. You think we're all getting used to it by now, don't you? But there we go.
Yeah. Can you see my screen right now?
Yeah, all looking good.
Okay, good. And hello, everyone, again. My name is Xinfei from the School of Management. Today, my talk is about the use of artificial intelligence in clinical trial management. Right, in this day, artificial intelligence has become an umbrella term, which include many different techniques from the math, statistics, and computer science. And specifically, the methodology I use fall into the area of operational research. So what it is, and from the name, you might guess it is the management subject, right? And actually, the operational research is the science of mathematical optimization, and where you formulate a problem into a mathematical model and solve it and translate the solution back to the initial problem setting. So the optimization is a tool which you can answer the question like how to optimally respond to the problem the decision maker is currently facing. So the second bullet point to show you a genetic form of optimization problem. And you might realize that optimization problem involves three elements. And the first is the objective function. So we can label it as the Z, which is the mapping from XY to a real value Z. So XY are the decision variable in this example. Of course, you can increase the dimension of the decision variables, but here for the simplicity, I assume the decision variable are two-dimensional. The second one is the is the optimization operator, so which can be either minimized or maximized. The third element is constraints on the decision variable. So figure one can give you an example of optimization model. So the light blue surface is the objective function regarding XY. And now we would like to find the global optimal. The block point located at 0, 0 indicate the maximum value 4. So this example actually is oversimplify the process of how to solve optimization problem. In the practice, only a few optimization problems can be solved within the reasonable time frame. So it requires a dedicated design solution algorithm to find the optimal or the near optimal solutions. So in practice, many business problems can be built as optimization problem. Given that I'm trying to maximize my revenue, given the resource constraint, how exactly would I carry out my business, of the value should I set for my decision variable? And the problems such as the scheduling, planning, supply chain management, or etc., are all about the optimization techniques. And another example maybe you are familiar with is the portfolio optimization. It's very classic in financial discipline, and where the objective function is trying to maximize the revenue and also try to minimize the variance, also called the risk. So background two. So in this research, the technique of the operational research is used to solve drug portfolio management problem. So let's look at the single drug development project first, and then we move on to portfolio optimization setup. So the drug development mainly requires the preparation of manufacturing supply chain, clinical trial scheduling, and management. According to existing studies, if you're familiar with some critical path analysis, you might realize that the clinical trial scheduling and management are on the critical path, but the manufacturing supply chain are not. So in this research, we only focus on the clinical trial scheduling and management. the figure 2 to show you the critical path activity in the drug discovery process. So we have 3 phases of clinical trial, and if we can pass all the clinical trials, we can submit the application to the FDA, for example. If failed at the any of those clinical trial, we have to get rid of this drug candidate from our pipeline. So now please look at the figure 3, which show you the drug development process, which is very lengthy and highly risky. Overall, it would take more than 10 years to get one drug approval. And the success rate, if you count, you are counting from the phase 1, and the success rate will be 1 in 5, around 20%. So that's the reason why we need to optimize the drug discovery process. And another challenging point for the drug development project is the economic value of a pharmaceutical asset is decreased with time. And this page will give you a reason. So first of all, let's define the formula to compute the pharmaceutical asset value. And the value is determined by the market share, the number of targeted patients, and unit price, and the discounting factor. So the first 3 is quite straightforward. I think is very easy to understand because they are related to the sales. But why we need to involve the discounting factor here? If you look at the figure 4, we can find that the sale drops sharply after the patent expire. And this phenomenon we call the patent cliff. So that's the reason. And normally the patent life is 50 years. That's the reason we need to try to complete the drug development process as quickly as possible in order to maximize the marketing life, and also try to recruit the investment cost for the company as soon as possible. Okay, move on to the portfolio setup. And so assume that a pharmaceutical company has a multiple drug candidate in their pipeline, and the resource like the budget, human resource, lab, or equipment is limited. So the company is considering how to optimally advance the clinical trial of different drug projects in order to maximize the overall economic value. So figure 5 is an illustration of clinical trial scheduling. And if we label those clinical trials as 1 to 9, and the length is the time required to complete the task, and the height is the resource occupation, then we need to figure out the optimal way to organize those boxes and given the resource constraint. Okay, so after the background introduction, the outline of the remaining is shown as follows. So I will briefly introduce the design of optimization model. Then the rollout and simulation algorithm will be introduced. Finally, I will show you some empirical results. So for the simplicity, I try to avoid involving too many mathematical notation in the presentation. So here, I only briefly introduce the idea behind the optimization model. So the model I use is the stochastic dynamic programming model, where the planning horizon is defined as T, and then the overall planning horizon is discrete into many time steps. And each clinical trial has certain success probability, and we need to try to complete all the clinical trial and in order to get the market approval. So to evaluate the economic value, the market share, unit price, number of target patients are all known. So we are also given the minimum resource requirement of each clinical trial and the overall resource constraint. We will make the decision at each time step as the project go on. And there are two groups of decision might be considered to apply. The first one, we can start a new clinical trial if predecessor trial is completed. And also we can increase the resource allocation for the ongoing clinical trial to accelerate the process. So it is the Monocot tree generated by the stochastic dynamic programming model. And the square, you can see we have a square, we have circle, and we also have some arrow line. So the square here is represent a state where we need to make the decision, right? And you can see that assuming that we start at the left-hand side and this state, and we have three potential actions here. The research question is we need to identify which action is better, or which action we need to select for the current state. Okay, and the challenging is, well, first of all, we don't know the decision at the future state. If without this information, we can't run the simulation. Another challenge is because the outcome of a clinical trial is uncertain, which means we have a lot of combination of clinical trial outcome. So we have two challenges here we need to resolve in this research. So to evaluate the performance action one, right, we need to select this action and run the simulation. And when we can see the uncertain information flow A1 here, and then we can move to the future state here. So we try to use a technique called the rollout. Here, I'm going to show you the rollout algorithm will tell us how to move at the future state. So the design of base policy is quite important because the base policy help up to determine the move at the future state. And it also will influence the estimation accuracy of action performance at the current state. And so we need to use the technique called Lagrange relaxation to construct the base policy. And this kind of technique provides an upper confidence bound estimation of expected total reward. And this base policy design satisfy the property we call the sequential consistent. So the overall rollout algorithm is guaranteed to produce the solution at least as good as the base policy alone. In the machine learning, we call the OneStep policy improvement. So now we start to address the second challenge in designing an optimal learning policy to reduce the number of simulation requests to identify the optimal decision. So we call this optimal learning policy as the statistically raising algorithm. And the raising algorithm is to address the ranking selection problem, where the number of different potential action is very large, and the random events have huge impact on the action selection. So in the statistical raising algorithm, we use two simulation techniques. One is the common random number. So the common random numbers means all actions are subject to the same random seed. It will reduce the variance of different between the action. here, try to give you an example how to use the common random number. And because we need to reduce the variance, also we need to reduce the number of simulation we might need. So we need to decide the learning policy here, which we call the statistical raising technique. So it is a design principle. We need to evaluate each alternative with a small set of simulation run first, and then to decide the alternative with the best mean. The best mean alternative will be the winner in the current race. So for each alternative, we need to estimate the confidence interval of the difference to the best alternative by using the empirical Bayes-Stern equality. So if we identify an alternative is significantly worse than the other, we will remove this alternative from the simulation in order to save the budget. So that's the idea we decide the simulation algorithm. Okay, here is an example how to use this technique. Suppose that we start with a very small round of simulation, and then we identify the action 5 with the best mean so far. Now, if action 4 is significantly worse than action 5, we will remove action 4 from the simulation. And then we keep running the simulation. Maybe in the next round, we identify action 2 and 6 are worse than the action 5. So we keep removing these two actions from the simulation. And then we let the simulation keep running and remove the action 1. And finally, we remove action 3. So according to our result, the raising algorithm can save 29% of the simulation budget compared to their equal allocation. I think the equal allocation strategy is the very standard technique. Assume that you have a different action, you just allocate the same time to each action to run the simulation. I think that's a common practice. Okay. Another technique we use is called a rapid charge, and which means if the best solution alternative is changed, we need to add back all the previously eliminated alternative to the simulation in order to guarantee the final process have some probability of correct selection at the end. So that's the reason we need to have this type of step. Okay, it is too mathematical. I try to skip this line. We can directly go to the empirical result. So in the empirical experiment, I have 3 different sizes of portfolio here. The small size, which involve 5 different job projects, and medium size involves 7 projects, and large size involves 10 different job projects. And we set the simulation target as the deserved probability of correct selection is 0.05, and the budget is 150 simulation per action. Okay, the benchmarking is decided by 2 industrial policy. The first one is a high success task first.
Sorry, 1 minute.
Okay, I will finish quickly. So 2 benchmarking policy here, and you will see that if we don't use any roll out and only use the base policy, and then we run this, the simulation, you can see that our simulation process can save the budget up to 40% 41% and also achieved a very better performance here. So you can see that our simulation policy actually helped to reduce the computational time. And if we apply further to use the rollout, which means we combine the base policy plus the simulation, and then we can see what happened here. And you can see that in all the test instance, our method achieved the best result. I think that's the end of my presentation today. Okay.
Thank you so much. Sorry to have to rush you at the end there.
Yeah.
If there are questions for Jin, do write them in the Slido, and we will compile them and share them later for him to respond by text. That's one of the nice things about Slido, that we can do this offline afterwards. So if it's okay, we shall move on to the next talk. So if you want to unshare, Jin, that'd be great.
Okay.
So the next talk is on pandemics and infodemics, the nature, extent and reach of public health misinformation on social media during the COVID-19 pandemic. And we're welcoming Luisa Zuccolo and Maria Sobchik to give us this talk. Luisa is Senior Lecturer in Epidemiology at the MRC Integrative Epidemiology Unit. She uses population health science and causal inference methods to answer questions about prenatal alcohol exposure and breastfeeding and lactation. She also has an interest in public health messaging and misinformation. And Maria is a research associate also at the IEU. Her main research is in genetic epidemiology and health data science. Prior to joining Bristol, Maria did a DPhil in Department of Plant Sciences at Oxford and worked as a bioinformatician as well. Over to you.
Thank you very much, Kate, for the lovely introduction. So hi, everyone. Thank you for inviting us to present this. So first of all, I wanted to mention that Dr. Cheryl McGuire led the project, and she got it funded. So thanks to her for this. And I'm here covering for her maternity leave. So I'm hoping to do a good enough job together with Maria. So soon after WHO declared the COVID a global pandemic on March the 11th, 2020, the UN and WHO itself actually declared the rise of an infodemic, highlighting the danger posed by the fast spreading of unchecked misinformation, and also started making the fight against misinformation the second of their pillar of work. Now, the dictionary definition of misinformation is the false information being spread regardless of whether there is an intent to mislead the public. Now, in parallel with research on the viral spread of COVID-19, some researchers started studying the dynamics of the infodemic, including analyzing viral tweets, for example, and other social media content. Now, misinformation has been an issue in public health for quite a while, as highlighted by some prominent scientists. And this spans several areas relevant to the COVID-19 pandemic. You all will have heard about the issues around vaccines and the misinformation around vaccines, but actually it's also extends to non-pharmaceutical interventions. So as a group of public health researchers in the population health sciences, we pivoted our interest in public health messaging, which is usually around health promotion. As Kate suggested, I study prenatal alcohol exposure, but also infant feeding and messaging around those topics. And we wanted to study misinformation around something that was COVID relevant, and in particular, which was face masks. So we chose this topic because we remember very well at the start of the pandemic in the UK, there was a lot of uncertainty, there was a lack of consensus among scientists and medics. And as the situation evolved, the advice about wearing face coverings changed quite dramatically and at different times in different countries, making this potentially quite a good case study of misinformation. So in the UK, we actually started back in March 2020 by completely dismissing face masks and their use in the fight against the disease. And it took a really long time before face masks became mandated. Now, this COVID-19 pandemic response timeline shows how late UK policy caught up with recommending mask wearing comparing to many other countries and official WHO guidance. And we only started talking about it at country level at the end of April, But it wasn't until the 15th of June 2020 that a mandate for wearing face covering on public transport and other public indoor spaces came into force. And for context, you can see here how, compared to countries elsewhere in Asia in particular, but also in Europe and in America, the UK, the uptake of face covering in the UK was really, really delayed. So as the evidence accumulated for the effectiveness of a face covering and the lack of damages associated with their use, it also shaped advice and it shaped communication around it in an effort to clarify the message and fight misinformation. So graphics like this became more and more widespread, suggesting what big difference face coverings could make, especially in certain contexts. Now, this project aimed to upskill us public health researchers in data capture and analysis methods applied to social media data research. We then applied these skills to work collaboratively with colleagues from research IT. Now we addressed nature, extent, and reach of misinformation on Twitter about the use of face coverings during the pandemic. And as I mentioned earlier, Dr. Cheryl McQuire, who's the second on this row of pictures, led most of the work. I'm covering here for her maternity leave. Doctors Christopher Wood and Mike Jones, number 1 and number 4, from Research IT, helped to develop the search strategy, and they helped us build a database. And then Dr. Maria Sobczyk was the analyst, and she will talk you through our preliminary results before I wrap up. Thanks, Maria.
Hi, so Mike from Research IT was instrumental in providing us with a database of tweets. We are issued with an academic license, which allowed us to fetch 10 million tweets per month. Initially, we tried to fetch using keywords such as face mask. However, they returned a lot of results, and often API couldn't cope with such a high load. So in the end, we focused on hashtags and not keywords related to mask usage, which were compiled previously. And we only used original tweets, no retweets or replies. This resulted in a corpus of initial 3 million tweets. The Twitter data is provided in a JSON format, which was then processed into CSV. And it provides us with a lot of metrics about tweets, such as number of likes, retweets, the popularity of the user as well. So we started off with initial 3 million tweets. However, we went down to 1,700,000 tweets posted by around 700,000 users because we had to filter out a lot of commercial tweets, which was done using both URL and keywords. Here we can see the timeline of tweet number through time. And as you can see, there are spikes in popularity of the topic, which actually coincide with mask mandate in the UK being introduced or changed, which is actually quite surprising because our tweets were sourced throughout the whole Anglosphere and were not focused just on the UK. Here we see the network of the most common bigrams, meaning 2 consecutive words in tweets, and they sort of confirm that we found relevant tweets related to coronavirus, stay at home, pandemic, vaccine, health, distance, glove, surgical. Then we looked at sentiment analysis, which allows us to look at the sentiments expressed in different tweets. It can be divided into positive and negative. And as we can see, positive tweets outnumber the negative tweets throughout time. And the proportion didn't change through time either. The sentiment can be then distilled further into specific emotions, such as sadness or trust. And trust actually dominated our tweets, followed by anticipation. Here we can see the top words which distinguish each emotion. And in some cases, actually, they align with a given emotion. So for example, joy is associated with love, sadness with pandemic, fear is associated with pandemic too, and infection, and so forth. However, we found cases of what are most likely to be false positives. For example, where is associated with trust, but in our context, where refers to wearing of masks, so it's not really talking about trust. And this is an interesting case. So it was at a time when Donald Trump was still president, and that's why Trump was picked up as the top word for surprise. Then we decided to do topic modeling using unsupervised and semi-supervised methods. For unsupervised methods, we use LDAA and top2vec. There was another method called Correx, which is enhanced LDA method, which allowed us to anchor specific topic on seeded keywords. In the end, none of the methods, supervised or semi-supervised, resulted in definition of discrete topics within each identified cluster. They were all contaminated with irrelevant tweets and often highly fragmented. For example, top2vec discovered around 4,000 to 5,000 different topics in our tweets. Whereas ourselves, we are interested in 4 preliminary hypotheses relating to mask discussion. The first one is, the first myth is that the masks are ineffective. The second one is that masks are actually restrict gas exchange, limit oxygen intake. And the following one was that the masks can cause further infection, not just COVID, but for example, because presumably due to moisture collected by face mask, they can then lead to some fungal infections. And the final one, that they can affect children in schools negatively due to problems with communication. So top2vec approach was very helpful in sort of helping us define a corpus of keywords relating to each topic, and which were then used in our manual keyword search to just give us a general idea of how many tweets were devoted to each topic. However, we didn't find many tweets related to our topics of interest. Out of 1,700,000 tweets, no more than 30,000 tweets were found to belong to a given topic. And these tweets also differed highly in popularity by like mean and retweet mean. Given our defined topics, we can then track them through time and see how their popularity changes through time. We can also do it by the like counters. For example, we can see spikes at certain time points, and then we can go back to see which tweets became viral and so forth. So here we can see again the sort of top diagrams specific to different topic, and even after a lot of filtering, we still find that a lot of diagrams are irrelevant. So, for example, here we find diagram for Ale, France, Germany, but on the other hand, we also find relevant diagrams such as respiratory droplet in the risk of infection. In limited gas exchange, we find oxygen intake, lack of oxygen, and so forth. So our main takeaways for mining Twitter data is that 10 million tweets for download per month is not a lot, but it's much better still than the commercial option offered by Twitter. We found a lot of hashtag hijacking. A lot of tweets were tagged with popular mask hashtags. However, they were totally irrelevant. We found a lot of ads which require a lot of data cleaning. Ads often present were not exactly duplicated text, but they exploited user mentions. We also found that Twitter language filter is not perfect. Our unsupervised topic modeling detected tweets in German, Dutch, Spanish. We also find that unsupervised, semi-supervised topic modeling is difficult due to short length of tweets and is more suited to longer text. And the conclusion is that mining Twitter with our hashtags didn't uncover many tweets with serious arguments against mask usage. Back to Luisa.
Thanks, Maria. That was fantastic. So Maria and I will be writing this up for the JGI blog. And we're also going to write it up as a scientific paper. But aside from dissemination activities, we'll be really keen to start an academic network, possibly within GW4, but initially at the University of Bristol, for colleagues interested in misinformation and health promotion, or misinformation and health in general in public health. So if anybody is listening here or watching in the future is interested, please do get in touch. We have earmarked a few people that we're contacting directly, but if anybody else wants to get in touch, please do so. Thank you very much.
Great, thank you. We have a couple of minutes for questions. I was just going to say in response to your last mention, so there is a GW4 data science network, which we've had a little bit of funding from GW4 to run a couple of networking events this year, and we hope to be able to take that forward next year as well. So it might be worth us having a conversation kind of offline about how you might leave a benefit from that network for your work. Are there similar kinds of research projects going on in the other GW4 partners?
I'm not aware of projects related to COVID-19 in particular, but I know that colleagues in psychology at Bath University are particularly active on social media messaging. And in fact, there is a GW4 funded PhD project, which myself and Professor Julie Barnett will be supervising from starting September, and that's to look at messaging around drinking in pregnancy and other substance use behavior during pregnancy.
Could you do the same kind of work? I'm thinking about the big misinformation topic at the moment that's in discussion is around vaccine hesitancy. And I wondered if you thought the methods that you've applied here could be applied to that topic as well.
So to start off, we wanted to focus on vaccines, but actually it's the topic that's most researched in terms of misinformation and disinformation. And behavioral scientists in particular have researched this a lot. Before COVID-19, it's been, it's possibly the leading research area around misinformation. So we actually have lots to learn from what they've done before and the take-home messages. So I think it's actually time to expand it to not just the reaction of health protection, but actually health promotion going forward.
Yeah, and the final question I had was around the multiple languages side of things. So you noted that actually you were getting quite a lot of non-English language tweets coming through with the same hashtag, and presumably you were excluding those. But I wondered if there was a possibility for a comparative study looking at across nations, or rather across language groups, as the kinds of misinformation that are happening in different languages.
That would be particularly interesting. And I would, to start with, I would actually shy away from automatic translation using AI for, software-based translation. So, I mean, thinking just of myself and Maria, for example, I mean, I'm an Italian native speaker, and Maria is Polish native speaker. So, if it was us, we could actually, for example, to take those two other languages and have a comparative study. Because as you say, cultural issues around misinformation are really important. And so what's happening in different languages would reflect different cultural environments. So it'd be interesting to do.
Really interesting. Thank you so much. I want to check from the floor if there are any other questions. Put your hand up. There's something that occurs to you that you haven't put in Slido. No? If not, we've got a break scheduled now. So just a 5-minute break. So if everybody could come back at 4:15 sharp, we'll get cracking on the next talk. We thought you might need 5 minutes to go and get a cup of tea or something. Hello, everybody. I hope you've managed to have just a few minutes break and get your cup of tea. I've got mine. So it gives me a real pleasure then to kick off this last section. We've got 2 more great talks to enjoy. And the next one is entitled Earth's Climate at Your Fingertips, Connecting Environmental Sciences and the Public Through Interactive Data Exploration. And we're welcoming Sebastian Steinig. Sebastian completed his PhD in 2019 in Kiel, where he studied the emerging ocean basins on the early Cretaceous greenhouse climate. He started as a PDRA in the School of Geographical Sciences here in Bristol in the same year, working on the super warm early Eocene. This is the last time in Earth's history when atmospheric CO2 levels were as high as those we expect for the end of this century. He uses coupled climate models to simulate the dynamics of these warm past periods and the interactions between the atmosphere and ocean. A better understanding of how climate systems adapted to these naturally high levels of greenhouse gases could help us to better understand and constrain future projections of anthropogenic climate change. Over to you, Sebastian.
Great. Thank you very much for the nice introduction and for the opportunity to present today. Okay, can you see my screen?
Yeah, that looks lovely. Great.
Okay, great. So, yeah, so pretty long title of the project, Earth's Climate at Your Fingertips, Connect Environmental Sciences and the Public Through Interactive Data Exploration. Or in other words, our project did not really start with a specific research question in mind, but it's rather, we wanted to build a platform, a website that allows an easier access to our climate model data for non-experts. And with we, I mean a couple of people from School of Geographical Sciences, from Earth Sciences, and the Seedcorn funding actually allowed us to team up with people from the research IT team. So for the outline, of course, I start with brief motivation for our project, how the Seedcorn funding allowed us to take this project from an idea to some actual prototype now. Briefly talk about technical implementation because it's first data week, so some people might be interested in this. Yeah, show a short demo of the current prototype that we have and end with an outlook of our future ideas. So as a motivation, I mean, I'm pretty sure that everybody attending the data week is pretty much aware of that we are dealing with constantly increasing amounts of volumes of data each day. And the increase actually of these volumes of data is quite hard to imagine actually, if you think about this. And this is particularly true also for research data and especially for my area of research, so Earth system modeling. This is true because our climate models, Earth system models become more and more complex. They have higher resolution. We do more simulations. Basically, if our computers get faster, we get more disk space, then we will do more simulations, basically. So it's easy as that. And for this, basically, there's one example here on the bottom right figure, a recent publication from our group, actually using several hundred of global climate models. The output of those, each of those has like output of several hundred gigabytes or terabytes of data, trying to reproduce or simulate like the climate evolution of the last 500 million years. So it's getting more and more data pretty quickly. But as these models get more complex and introduce more, simulate more subsystems, they actually get also more interesting to other disciplines out of like the core modeling community. So for example, meteorologists are interested in seeing how the climate dynamics of these past time periods, these greenhouse climates during, for example, the Cretaceous worked, what we can learn for future climate change. Oceanographers are interested in how these different ocean configurations during the past changed or influenced the ocean dynamics. Biologists interested in figuring out how climate evolution, how climate change might have influenced like the evolution of certain animals, or geochemists, geologists interested in how the environmental conditions influence the formation of sediments and rocks during the past. So as you know, like really accessing and making use of these large amounts of data actually needs a lot of skills and experience in the data processing. And probably a lot of you during this data week learned some new skills in this, but the reality actually is what these people will do is they will just write you an email and ask for the data. And basically you have to do a lot of processing to and distribute the data to them, because it's really a lot of work to start learning, like using command line or Python or whatever, to process the data. And we're really happy to do this, to share our data and do a bit more extra work. But you all know that this doesn't really scale, and especially not if you think about where the amounts of data go currently and in the future. This will not scale for the future. On the other hand, there are actually existing technologies on the web, especially, that already allow data access and data processing on every browser, every modern browser, without any additional software installed, even on your smartphone. Like several examples, probably most of people are familiar or have used for actually Google Earth, which is sort of this virtual globe, and which makes it really easy and intuitive to access large gridded data sets of geospatial data very easily. It's just a lot of fun to play around with this. Another example that I particularly find always interesting, I showed here on the right side, is the Earth Null School Earth Wind Map project, showing near real-time meteorological data, wind speeds around the globe, again on a virtual globe, very easy to manipulate data. And basically this already also got like a lot of media coverage, because it's in very intuitive access for people to enjoy, and the actual beauty of this data that we produce. So there's, I think, huge potential with these virtual globes to both make this data more accessible to other disciplines within academia, but also for public outreach. And actually this Earth Wind Map project really started the idea for our current project, because I always thought, like, okay, well, they display some sort of like global weather data, and basically our climate models produce very similar data. So it would be really great to take the software, because we saw this is open access available on the web, and put in our own data and see how it goes. But there was always one problem left, basically, and this is like that we are, in the core, we are scientists and not software developers, right? So we sort of have an idea what we want in the end, what kind of application we want to have and what we need, but really how to put this in form of a website, how to put this on the internet is something that is not our daily business, at least not for most of us. So this was always a barrier. So the Seedcorn funding really helped us in this case to get this idea into actual software. And this was supported by an actual professional software developer, and right from the start of the project, and this was invaluable contribution. So this was done in collaboration with the Bristol Research IT team. I just wanted to mention this again. I don't know whether everybody is aware of them, but they actually provide professional software development within a university context on a consultancy basis, and it's a really good experience to work together with them. And what they did is basically something that we probably should have done more carefully beforehand already on our own, is they screened like the repository of the software we wanted to use for our project, and they raised some eyebrows there initially, and they actually saw that, for example, if you just look here at the red box, the date of the last changes, last updates of the software is like 5, 6, sometimes 8 years, and which is like, I think, ages in terms of web development. So it would really take a lot of effort to, first of all, update those, all these, the different libraries and so on, to really start working on like a longer term project. And in the end, basically, we decided this would take too long, and actually we decided to write a new software from scratch with the help of the research IT team, and they all helped us with implementing the whole development workflow and hosting of the website, which was a great experience. Just one short slide about the technical implementation. Maybe some people are interested in this, what we're doing now. So what we wanted to have is like a one-page website, which we call an application, which would run again on any modern browsers without any additional software that you need to install. The idea is just you see a link on Twitter, you click on this, and then you can work with this on your smartphone, on your tablet, wherever you are. If you look at the GitHub page, basically most of this is now written in JavaScript, and especially in a 3D library called 3.js. And what this basically is a library to enable 3-dimensional visualizations on the web browser. And this is basically spot on what we want to do, because we are simulating this three-dimensional world, which is the Earth, with our models. And so it would be actually best to just represent this in a three-dimensional world, our model data, because this is something everybody can relate to and understands intuitively. What's also important is using like a WebGL renderer. What this means is that it's basically running mostly on your GPU, not in the CPU. When you make a figure plot with Python or so, you normally do this on your CPU. The 3JS uses the GPU to have like a lot of parallel power for real-time animations in the browser, and it's really crazy to think what these even modern smartphones are capable of doing in the browsers at the moment. And just for our model data, basically, we encoded everything into sort of like PNG images that you can see on the bottom, some sort of like, think of a movie strip that we can play in the browser, and we can easily push to the graphics cards for data visualization. And yeah, because I don't want to throw in any more technical jargon there, I just wanted to show you just a brief demo of like the current prototype that we have, because I think that makes it easiest to understand what we're trying to do here. And just share another screen. Okay, so I just opened the current view in the web browser. So this doesn't look too exciting at the moment, but I just slowly built this up to just give you an idea about what our idea is here. So we're trying to display the climate model output data for the last 500 million years, which is called the Phanerozoic time period. And we started something like 500 million years ago. And what you can see here is the figure of the paleogeography. So blue means ocean, green land areas during the early Cambrian. And this is more or less what you see is, yeah, what you would normally get a normal two-dimensional figure. And I just start maybe some animation to time, so we're going more and more closer towards present day here. And when you start with this, it's more like a simple view what we had before. Basically, we're always producing figures, maybe with Python or something like this, and then we put those together for some sort of like animation to give some sort of idea about time evolution. But what we can do with these modern libraries and GPU acceleration basically is, for example, we can very easily use a time interpolation on any web browser and basically just give a very smooth representation of this time now. Basically, we can always on the fly interpolate the time between different model simulations that we performed. And the thing now is that we are not talking about a two-dimensional figure that we would normally produce, but we have a two-dimensional figure on a plane, basically in the 3D space. So this is just like a plane in the space, which means we can manipulate like the geometry of this plane very easily to help us to give more information about the display basically to the user. So if you look at the geometry of this plane, it's made up of a lot of triangles basically, where we can, and then a figure that is basically put on top of this geometry, and we can easily change the position of these triangles to, for example, in this case, represent the elevation that we actually in there. And we can do this very easily in the web browser as well, and just, for example, exaggerate the topography to give the user an idea about how the ocean basins looked during the time. And we can then start to add several layers basically of data. Think of something similar to, for example, like Photoshop, where you would just add, in this case, like maybe SST data or another layer for the atmosphere in this terms of precipitation. And all of this basically is controlled by our global time control. And these are just different layers that we put together. What we can also do is would prove very efficiently in communicating dynamics are these particle animations for ocean currents, for example. We can easily add those to our scene basically, and showing like these ancient circulation of ocean currents. And all of this, yeah, we could change basically the projection to change something like to a Google Earth view, what is more familiar with people, for people basically, where we go to just something like a globe. Just get rid of the atmosphere here. And then you can always go around the Earth, zoom in on any region that you're interested in to get basically more details about the ocean circulation for the whole last 500 million years, basically. And especially on something like a touch screen or tablet computer or something like this, this is really, yeah, I think, a very intuitive way of accessing all the data that that we produce, basically. And yeah, all this is fed basically by, like I said in the beginning, of the 109 simulations that we performed, and we put the output there basically on the web. And now people are able to just click on any time period they are working on to get a first idea about how the circulation maybe looked during the, let's say, like Cretaceous, when the dinosaurs were still around, to see how different it was from the present day. Yeah, I think we think this is a real powerful new tool basically for our field. And to just go back to my final slide here from my presentation. So should work. I don't know, can you see my screen again? The presentation again? I don't know.
I'm seeing a screen that says demo, just as demo of climate. Yeah, it's a slide.
Okay. Okay, so yeah, just to wrap this up, I don't know whether you see the screen or not, but anyways, what I want to say is, like, basically this is our current prototype. We are happy with this. We are focusing still on, of course, like a lot of like user interface, and give some guided tool for people who are new to the topic to just understand what they're actually doing here. And we hope to have some sort of like a public release in autumn to really showcase the potential of this. But and we think really this is the interesting thing about this tool, is that it's basically interesting for a lot of people. So it's really interesting for other researchers that are not non-modeling specialists, basically, to discuss their ideas about research. It's great for educational purpose. So if you talk to students about this, trying to learn about past ocean dynamics, for example, it's great. And of course, always also for any type of public outreach. So, and just the last thing I wanted to mention is probably like a long shot here, but given like the diverse background of all the people here on the call, but this is ongoing open source project. So I'm never tired of asking, like, there's always a chance to contribute to this. If you ever always wanted to build something like this, or you have like the data in mind that you produced that you always wanted to show in some sort of way. So it's never too late to get in the boat and contribute to this. So thank you very much for your attention.
Thank you so much, Sebastian. I want to have a play. That's my thing. It just looks great.
Yeah, it's a bit problematic for the development, actually, because like always when we implement some new feature, we always get lost in just playing around, and yeah, it can get mesmerizing.
Yeah, so I can, is it if you're using it for communicating with other people in your field,
Exactly.
are you able to, are the users able to kind of to sort of click on a number of parameters, find the parameters they want, and then access the data that underlies the visualization? Or would they need to then go back to you to egress those data?
Yeah, so the whole idea of this project is, of course, to really like remove me as the middleman out of this. So basically to give this tool to people so they are able to perform some data analysis on their own. Of course, it's like if you really want to do some fancy statistics, then you will basically probably download the data otherwise and do it on your local machine. But really to just go somewhere to extract, I mean, for our time, it's really, for our research field, it's more or less like people work on a specific time period, a specific region. They want to understand like temperature evolution there. They can easily navigate there and at least access the data from this one suite of model simulation that we put up there. Of course, there's always room for improvement. So basically the idea is at the moment to really have like this one showcase with this one set of model simulations that we want to produce, and then use this as a sort of like proof of concept for future proposals to really add more functionality. For example, like what we really want to have like is like a real API there, basically, when so that this website is more or less like your user interface to tell our database, okay, I'm interested in this region, this age. So basically give me other data sets that are relevant for me basically as well. So this is hopefully some plans for the future basically, but yeah, not for the Seedcorn phase basically of the project.
No, really, really interesting. And the other immediate kind of use case I could imagine going forward is exoplanets. I know there's a growing community of researchers across the UK, particularly who are working on general circulation models of atmospheric conditions in other planets in our solar system and beyond. And this would be a great way of communicating their work to the public.
Yes, it's also actually in Bristol. So in our School of Geographical Science, there's, for example, like the working group from Dan Mitchell working on exoplanets as well. So we already talked about this ideas. Of course, like visualizing like atmospheric dynamics of other planets is very interesting. And it's in the end, so this is more or less to showcase like the type of model data that we produce for the Cretaceous and for exoplanets is very, very similar. And so the output is very, very similar. So it's very easy to adapt this software to show other things. And we just decided to start with this, like this paleo climate. And of course, like the there are like endless of options probably for the future.
Really fantastic. Thank you so much. Any other questions? Hope I haven't missed anything. No? Okay, thank you very much, Sebastian. In which case we move to our last talk for today, which is titled Effects of Adolescent Physical Activity on Physical and Mental Health in Adulthood, Novel Multivariate Pattern Analysis of the Intensity Spectrum. And giving the talk are two colleagues, Ahmed El Hakim and Matteo Sattler. So Matteo is a psychologist with research interests in physical activity epidemiology, the measurement of physical activity and its effects on mental health. He did his PhD at the University of Graz in Austria and will be in Bristol to work on the longitudinal relationship between the intensity of physical activity and various mental and physical health outcomes in ALSPAC. And Ahmed is a senior research associate in epidemiology, working on the EU-funded Life Cycle and Long Tools projects. His research uses large multi-cohort collaborations to study the determinants of cardiometabolic and musculoskeletal health trajectories, and his current research includes studies relating to medically assisted reproduction, pregnancy complications, pubertal growth, physical activity, and environmental exposures. And Matteo, are we starting with you? Yeah?
Yes, yeah.
Great, over to you.
Thank you. So, is it working?
Yeah, looks good.
Okay, great, thank you. So, good afternoon, everyone, and thank you also from my side for the opportunity to present some aspects of our project in this session. Yeah, so as you said, our project is on adolescent physical activity, on physical and mental health in later life, and we are particularly interested in the intensity of physical activity and how it relates to health later in life. And we are considering a novel kind of multivariate pattern analysis for the physical activity data. We're still quite early in this project, as I just recently came back to Bristol, so I'm rather staying with the idea and the methods of this project, and why the Seedcorn funding will help us to maybe make a substantial contribution to our field by considering a different approach for this physical activity data. So it was Ahmed El Hakim and I originally starting this project, but we are closely working together with experts in the field of epidemiology, sports science and psychology from Bristol, from Graz, Austria, where I come from, and from Norway. And I would just go like very few background slides explaining the problem we have. So I think we can kind of skip that slide, but we know that physical activity is important for our health. We have really strong and high quality evidence nowadays for different mental and physical health outcomes, and the inclusive kind of public health message today is that we should not be still for too long. So every activity counts in that sense. And so we know that, but still physical activity is quite complex. It is a multidimensional construct. So we can be active in different settings. We can be active, you know, in work and leisure, etc. We can be active with using different activities and involving also different intensities. So we can, of course, being rather sedentary or light or moderate or even more vigorous activities. So, and in this project, we are particularly interested in the intensity of activities and how that is related to health. And which data are we going to use? So when we measure physical activity, we can of course ask people how active they are. We can ask them questionnaires or let them fill out diaries, or we can use devices such as accelerometers. And I think you are all familiar to kind of the accelerometer approach. So we have that on our smartphones, we have it in the activity tracker, so we can track the daily steps. And they measure basically changes in velocity over time in a certain time interval. So usually multiple times in a second and over several days. So we get a lot of data out of the accelerometer measurements. And we can use this accelerometer information, which is collected, to get estimates of especially also the intensity, the average intensity of the activity. And we start with kind of rather or either activity counts or even raw gravitational units nowadays. And as I said, we get that every multiple times in a second. We can average them over time intervals. So we often use like 5 seconds or 1 minute averages, and we can get like activity counts for each minute. And high activity counts, as you assume, means on average higher intensity, or we assume that this activity or this movement was also did also involve higher intensity as well. And we use this activity counts then to classify the intensity for each time interval, and we may make this by using cut points derived from different calibration studies involving also physiological measurements. And we can then say this minute was rather sedentary, light, moderate, or vigorous, for example, based on these counts per minute. And as you see, higher counts mean higher intensity. But what we in physical activity research did for decades or for years, we are working with the accelerometer data and also several data, is that we use only few and very broad intensity categories in our statistical models. So we often use just a summary measure of moderate to vigorous physical activity, so the two latter categories from the slide before combined. So this means we rely really strongly on those cut points, on single cut points. And it also means that we collapse a lot of activities in the same group. So you can think of brisk walking maybe and playing squash. It's in the same group, combined in the moderate to vigorous physical activity intensity group. So we have only a very limited resolution of the data. And we also not really focus on other intensity parts, so such as light physical activity, where we also have a lot of useful information, because we're doing, of course, a lot more in those lower to medium or moderate intensity range compared to the vigorous part. And this also means that we cannot really detect the relative importance or influence of certain intensities compared to others. But the problem, or actually maybe the reason why we're doing it, is the data itself. So the physical activity data has a closed structure, so we only have 24 hours a day. So it's limited, and the variables itself from a behavioral point are correlated with each other. So we have multicollinearity in the intensity variables. So which means that time spent in intensities which are closer to each other are more correlated compared to intensities which are further away. So let's say a light physical activity and very light physical activity, the times you're doing it in these intensity categories, they are more correlated compared to light physical activity and vigorous physical activity, for example. So, and we all know these collinearity issues can cause serious problems in our standard, let's say, multiple regression models, which we often use in physical activity research in epidemiological settings. And so there's a need to use like different approaches now to deal with the data, the physical activity data. And one approach is, so there are nowadays different ways or approaches to handle the closed structure and the collinearity. And one type of analysis is multivariate pattern analysis, which actually partially squares regressions. So perhaps many of you are aware or know this technique. And it's often used in other fields and was developed also for other fields, but just recently applied to physical activity research in late 2018. And this method has several advantages and also, of course, some problems and assumptions which need to be considered. But the main advantage for our purpose is that it does not make assumptions regarding the distribution and correlation between the predictors. And so we can really include several intensity variables in the same statistical models. So that's the main advantage of this model. And what partially squares PLS essentially does is it tries to deal with the collinearity problem by reducing the dimension by creating orthogonal linear combinations of our intensity variables, of the predictor variables. So it is, as we know it from like other factor analysis, principal component analysis, and so it's the same kind of principles, but it does this while simultaneously maximizing the covariance with the outcome. So that's the different thing, I guess, where we can distinguish this to the traditional factor analysis approach. And so it tries to maximize the covariance between components in the X space kind of and components in the Y space. So it's a multivariate approach, and it tries to, or it actually includes all the intensity information at the same time. So it looks at the association pattern rather than what we do in traditional multiple linear regression, focusing on the individual or unique contribution of individual variables. So that's, I think, the main differences. What are the main differences here? And when this PLS was applied in 2018 to metabolic health in children, we can see that, so we can include all the intensity categories. So when you remember from a few slides before, we often use this like MBPA or 2-3 broad categories, but we can use smaller intensity band categories. And we saw, or the Norwegian group saw, they introduced it in 2018, that light physical activity and sedentary behavior is not contributing as much, and not really much here compared to the higher intensities when it comes to metabolic health in children. So we can see that the contribution to our outcomes, health outcomes, is increasing with high intensity, with higher counts. And you can see the selectivity ratio here. That's just explained variance divided by residual variance. And so you can get this overall association pattern with this approach. And they also showed that they can explain around 13-14% of the variance in metabolic health, which is also higher when we compared to only using like a few broad categories. So what we would like to do in this project is we would like to use, or we're going to use PLS to explore the associations between the physical activity intensity in early, middle, and late adolescence, and mental and physical health outcomes in adulthood, namely at age 18 and 25. So we would like to identify intensities which are relatively strongest associated with future health. We would like also to identify differences in association patterns between different health outcomes, and to look at the contribution of sedentary time, and of course, in general, how relevant is this entire intensity profile for our health outcomes. And we will use physical activity data collected in the LSPEC study, which is, you all know about it here in Bristol, which is a famous world-leading birth cohort study, and they collected several health and also physical activity parameters over time. And so we are going to reanalyze physical activity data from age 12, 14, and 16 and combine those to derive our intensity categories, and combine those to get a more kind of robust indicator of adolescent physical activity rather than just using like a single wave of physical activity data. And then we will look at different health outcomes in the future you can see the list here. So we usually focus on 2 or 3 major outcomes, and to see how strong the association will be in terms of the intensity pattern. And personally, I'm interested in differences in association patterns, for example, between mental health outcomes and rather physical health outcomes. And yeah, so that's, I think, our project on which we are going to work over the summer while I'm here in Bristol. And that's basically it, the presentation. And I hope I'm on time. And so thank you very much. I hope you can still hear me. Or,
yeah,
sure.
fabulous.
Okay, cool.
Yeah, yeah.
So thank you. That's it.
We're all here. Yeah, great. So I have a question about the physical activity data from the Ausbach, and Jason, I should say, very nice for us to finish with a project working on Ausbach, us being the Jean Golding Institute and all. So that's a really nice link. So for the data from 12, did you say 12 and 14-year-olds about intensity of physical activity, is that data which is from surveys, clinic surveys is the first question. And secondly, is it self-reported by the children or is it reported by their parents?
So the physical activity data is collected, I think, during clinic visits by accelerometers, so by the devices. So between age 12 and 16, yeah.
Okay.
Yeah,
okay.
so they were asked to wear the device for up to, I think, 7 days during waking hours.
So it's just the accelerometer data. There's no kind of narrative from surveys.
I think there are not on each wave. I think they also collected self-reported information. That's right. So we're not going to use that.
I'm sure I've seen data on the sort of sporting activity and that kind of stuff at school.
I think this data is available, but in this project we are only focusing on the device-based measurements, because because the same model was used, we can combine those, and yeah, so that's what we're trying to do.
Really, really interesting. I hope you have a great summer ahead of you. Anybody else got a question for Matteo and Ahmed? Pretty sure Ahmed's in the room. Do you want to just put your video on, Ahmed? Say hello, so we know you're here. If not, there's a
better
question.
not ask.
There was additional question in the. Oh, there you are. Hi. Thank you very much for coming. Thank you very much for contributing to the work. It's great to see. There was a question in the chat. I put it in the chat for Zoe, actually. If you're still here, I'm just checking that you're still around. No, you went to look. You went to pick up your daughter, didn't you? I'll send it to you. It was a question about whether the versions of the data set were made available. I'll send it to. We'll sort that out offline. We can do that probably, and then send around to participants an answer. I know we can do that. We have the technology. So any other questions then for, in fact, any of our speakers or anything that's occurred to you along the way? I'm just checking, see if I can see a show of hands or anything. In which case, what I think might be quite nice, if we could just flick our videos on for 1 second and give the speakers a virtual, slightly silent round of applause. I think that would be really nice. It's so hard, isn't it, when these kinds of events, but really, really enjoyable afternoon. Fantastic insight into the projects that are ongoing, and it's one of the real pleasures for us working at the JGI that we can support, even in just a modest way, to seeing these new collaborations and new research areas bubbling up within the university. Absolutely fantastic. Thank you so much. You might remember from my introductory slides, I mentioned the showcase on the 17th and 18th of February 2022. We might well be kind of offering some opportunities to present some of this work at that forum as well. So bear that in mind as you take your projects forward. So that's the end of day 5, last event of Bristol Data Week. I have mixed feelings. It's been, yay! It's been the most amazing full-on week for us all, and participants included. And I have it on hot off the press, I think, Lily, that we've broken the 2,000 boundary. Is that right? You're on mute. Yes, yes is the answer. So we welcomed more than 2,000 participants confirmed, so which is absolutely a great result and just shows how much energy there is in data science and data intensive research, not just at the university, but in our region and internationally. We know just from having a look at participants that we've had a really international field, and lots of people from outside the university as well as from within taking part in our activities. So that's fantastic to see, and we hope to build on that in the future. Okay, thank you everybody. Have a lovely evening, have a nice weekend, and we hope to see you at the showcase, or not, if not that, before at one of our other events. Thank you so much.
Thank
Bye.
you. Bye.